because we know if we have operator, we know we need to know what is the commutation relation of property of this operator, and then what is the eigenvalues, what is the eigenstates. Right? This general ask ourselves. So now we are going to answer those questions step by step. So now let's answer the first one. Let's first double check if the additional two angular momenta still give us another angular momentum. So let's look, because by definition, right? So because G is G1 plus G2. And G1, G2 itself, they are angular momentum, right? So then it is vector, so that is G1x plus G2x, x components plus the y components, each individual, and the z components. Right? Just simply add together. No product. So, and then you can see here, this, I'm going to say it's Gx, because these x components are total, right? This is the Gy, this is Gz. So yes, we can write, it is vector, right? So that we immediately know, okay, it is vector because it has three components. Here, Gx is G1x plus G2x and Gy, G1, G1y, G2y, and Gz is G1z plus G2z. So if we want to ask to find these components or total angular momentum, just simply add this each individual, right? So yes, it is a vector operator. So we answer this. Where the components is simply add together. Now that is the first condition. It is after a vector operator. Now next one is key, right? Yes, it is vector, but this vector components follow this commutative relation for any arbitrary this angular momentum that we need to prove ourselves to check, right? So now to answer the second one, let's look. So that is then now let's look at the second one, because since we have already the component Gx, Gy, Gz, right? So now let's look at Gx and Gy. If Gx, Gy equal to I, H bar Gz and others, so then that case follow this, right? So now let's look at this. Gx, Gy, Gx, G1x plus G2x, right? And Gy is G1y plus G. Oh, I think there's a pre. Okay, I think so far it is there's no component. Okay, so that is fine. So we have. Let me first write down here. G1x. G1y plus G2x, okay, G1x, G2y, and plus G2x, G1y, plus G2x, G2y. All right. Okay, I think I need the first give the condition now. The condition or the properties. Well, the G1 is in the subspace of 2G1 plus 1. Because G1 is one of the either spin over output angular momentum. They do not over the independent, right? Or in this case, also we consider they are independent and G2 is another subspace. So they are independent. They are in a different space. Independent means that they commute each other, right? I'm going to use this vector here. That means include all the components. Okay, this one is not good because I remember last semester we have the commutator. That is, and my students say, okay, that is S, S, N. So S, S commute, that's equal to 0. It is not. Since we know this one is S, S, right? Not inner product, not cross product. So that's not. But this is scalar, that is fine. So now I'm going to write this way. Independent, right? So now the J1, okay, J2, J, K, J is all the components. Because they're independent, so they commute each other. That is the first condition. Without this one, we cannot go over. That's because we have two different space, subspace. Like spin. Spin is limited or defined in the spin, that the subspace, and then up to angular momentum in the spatial space, right? So the independent, therefore any components between these two are commute each other. Okay, so then now we can adjust this one, and then now we can come back to here. So G1x, G1y do not commute. That's not commute, right? So this is I, H bar, G1z. This one, G1x, G2y commute, right? Because here, since they do not they are independent. And G2x, G1y also. So now I'm going to plus 0, plus 0. And the last one is I, H bar, G2z. So I, H bar, G1z plus G2z is Gz, right? Is here. Then initially we are looking for the commutation relation of Gx, Gy. It is equal to I, H bar Gz. That is angular momentum, right? And similarly, we do not need to prove, but you can prove yourself. For example, Gy, Gz, I, H bar, Gx, and Gz, Gx is I, H bar, Gy. So that means we have this equation in chapter 5. Yes, so it is angular momentum operator. That is, we first double check the addition of two angular momenta. Yes, I give another angular momentum because it is operator, is a vector operator, and also satisfy this commutation relation of angular momentum. Now we go to the second question. Second question, how are we going to express G squared? You may ask why we are interested in G squared, and since we are going to go to here, eigenvalue, eigenstates, so we need to find the mutually commute operators. Then we can find the joint eigenstates. Then associated with that, we can determine eigenvalues. So that's B. Since it's angular momentum, right? We know angular momentum operator G squared commute with Gx or Gy or Gz, but we just select one pair. For example, G squared with Gz or G squared with Gx. So by commuting, we just select G squared and Gz, right? That is here, right? We go to here, since they commute each other, then we can find their eigenvalues and eigenstates in terms of J1, J2, which we know. So now that is why we are going to see how to express G squared, right? So now, second. To express G squared, there are two ways. One is in terms of G1, Gy, G1, G2. the terms of G1, G2. Another is in terms of G plus minus and Gz. Right? So that is, so now let's do that. Because G squared, if in terms of G1, G2, that is definition, it is G1 plus G2. Inner product is G1 plus G2. So that is, now we pick the product. Here, G1 is G1 squared, right? Then G1 to G2, so we have G1, inner product is G2. And then G2, inner product is G1 and G2 squared. This 2, 5, this is square. About this product here. So now let's go to the details. So now I'm going to write G1 squared plus G2 squared, the first one and last one first. Now this one is, I'm going to directly write down and give you a brief. Okay, so here the first one, inner product, so that's G1x, G2x plus G1y, G2y plus G1z, G2z. That is G1 first, right, and G2 second. This one G2 first, G2 second, but since they commute, so the position will commute, that means G1x, G2x equal to G2x, G1x, right? So here I have a vector 2 here, vector 2. Then I pick the z component outside, because this is since we consider the G squared commute with square terms and z components, but the x, y, they do not commute, so we are going to replace this one by either Gz or plus minus, since we know G plus minus applied eigenstates give us is raising or lowering, right? So we can play with that. So now keep this one, I'm going to say this equation 1. We're going to deal with this term. Second one is G squared, because G squared, G is vector, right? So it is Gx, Gy, Gz, the inner product of itself, these components, right? Gx, not the individual. This is the total, but the component. So that easily we can, let me just write down here, Gx squared plus Gy squared plus Gz squared, right? Well, again here, Gx, Gy does not come in with Gz, so we are going to manipulate to replace Gx squared plus Gy squared in terms of either G squared or Gz or G plus minus. So we are going to deal with this. Now you can see here the first equation. I write the G squared in terms of each individual angular momentum, right? G1, G2, G1x, G2x. But the second one is in terms of the components itself. So there are two ways, depending on which one you are interested. So let's work on this. That's for equation 1. For equation 1, we are going to see how to replace this G1x, G2x plus G1y, G2y. Now, this one, we need to remember in chapter 5. Because, let's remember, so G1 plus minus multiply G2 minus plus. Okay, by definition, minus plus, plus minus is G1x plus minus I G1y, right? G2x minus plus I G2y. So then we go to details. So you have a G1x, G2x, and then this one is minus plus I G1x, G2y, and then this is plus minus I G1y, G2x, Then this one minus, yes, I is minus, right? Then here, this minus became plus, and this minus is also plus, so that's plus J1y, J2y. Okay, so we have these 4 terms. Then, so now, look this, J1 plus multiply J2 minus plus J1 minus J2 plus. Since here I have 2 terms, right? Either J1 plus J2 minus or J1 minus J2 plus. So, and then this one is here. Then you will see, because they commute, right? They cancel, right? So if these are placed, so this minus and this plus will cancel. This one my plus minus will cancel, right? So the only remaining is J1x, J2x plus J1y, J2y multiplied factor 2. So now you can see these 2 factor 2 of this J1x, J2x, J1y plus J1y, J2y is nothing but this addition of J1 plus minus or J1 plus J2 minus. So now the equation 1 rewrite is J square, the total angular momentum J square, here, J square is equal to J1 square plus J2 square. And keep here, this is still factor 2, J1z, J2z. And the remaining is J1 plus minus, right? So that is J1 plus J2 minus plus J1 minus J2 plus. Okay, so now there's a new equation. I'm going to say equation. That is equation 1, very right. So this is important we're going to use in the later. Next one is another equation 2, right, in terms of its own components. Okay, so now let's consider for equation 2, we rewrite. So now we are going to deal with this one, Jx squared plus Jy squared. Let's again we consider, let's look this J plus minus multiply J minus plus. That is Jx plus minus I, Jy, and multiply Jx minus plus I, Jy, right? So we have a Jx squared, and then you have a Jx so minus plus I, Jx, Jy, and then plus minus I, Jy, Jx, and then here again this is a plus Jy squared. So Gx squared, Jy squared, and this one I'm going to take this one minus plus I outside. I just need it, so now this is a Gx, Jy. Right? If you take this outside, so this is a Gx, Jy minus Jy, Gx. So that is commutator. Then that is IH bar Jz, right? So immediately have this IH bar, so this is a minus became plus. Right? So then this Jx squared plus Jy squared plus minus H bar Jz. Yes. Okay. So now this term, this is we are going to deal with this one. Therefore, Gx squared plus Jy squared is, we move this term to the left hand side. That is the product of J plus minus multiply J minus plus and minus plus H bar. So we have equation 2 J square equal to J square, okay. Let's take the Jz. That's Jz square first, right? And then this one, that is plus J plus minus multiply J minus plus, and minus plus H bar Jz. Okay, that is equation 2. We write equation 2. But we can also write another way. So now this one, sometimes we also need it, so just keep in mind. Another, because J plus J minus plus J minus J plus. This product, so then you can see here, it is this one. So if you add together, this term disappears, right? Because it's plus minus. So that equal to twice of this. This is immediately got to twice of Jx squared plus Jy squared. So you can rewrite the J squared also in another way. It is Jz squared plus this one, right? Half of J plus J minus plus J minus J plus. This is another equation, number 2. So these equations later when we might need one of them, so just let you remember those how to express. So we finished this one. Now we're going to go to this one. This one is complicated. So let's try to remind you what's each individual angular momentum. Can I erase this part? Not yet, right? Okay. So then
in the middle,
yes.
equation 2.
Yes, this one?
Yes. Is that J hat squared?
Yes, Jz squared. You mean
Z,
Z squared?
okay.
Jz, yes,
Z,
sorry,
okay.
Z. Sorry.
I was trying to figure out where the B came from.
not B, sorry.
You're fine.
Okay. All right, so let me erase this part. But you remember the question, so I think I need this space. Finish question 2, right? So now we go to 3, the commutation relations. To do that, we need to remind ourselves each individual in chapter 5 as an angular momentum, what is the commutation relation, then we are going to apply those. So just remind ourselves. Okay. J, let's do this way. I'm going to say J square, J1 square commute with any component J1, right? Or J1Z, okay, equal to 0. J is X, Y, Z components. That we know. We know the J square always commute with each individual component, so J1, J2, the same thing, right? So that is commute itself. J2, J equal to 0. That is the first. J square commute with its components. Second one. In the second one, we just use actually the same thing here. J square because they commute each individual, right? So that we will J1 plus minus. Because J1 plus minus Gx plus Ix plus I J1y, right? So that is immediately how it is. J2 square also commute with J2 plus minus. So that is one group. It's group 1. We need it. Group 2 is the J1 plus J1 minus this commutation relation, if you remember in chapter 5, it is 2h bar j1z. Similarly, j is divided by j2 plus j2 minus is 2h bar j2z. Then that is group, so this is a j plus minus. Then we have a j plus minus jz, j1 plus minus jz, j1z is equal to plus so j1z, j1 plus minus, it gives us plus minus h bar j1z, j1 plus minus. And the j2z, j2 plus minus, j2 plus minus h bar j2 plus minus. It's the second group. Okay, third group is the condition which I already discussed. Okay. Number 3 is that since they independent each other, the j square is j1 any components of j1. Let's use j2k commute. So jk are x, y, z. Since it's independent. And then also their square also commute with j2 0, j2 square j1 j1 equal to 0, and also the square j1 square commute with j2 square. So those commutation relation we needed. Now we are going to look the others. Since we are going to find what is the mutually commutative operators, then we are going to form or find the joint eigenstate. That is our goal. So now let's look. We are going to check. First one is j square. J1 square with jz. So jz is the component of total angular momentum, right? Addition. With each individual angular momentum is a j1 square. So j1 square is let me just give a j1 square. Jz is j1z plus j2z, right? Then we know j1z commute j1 square. That is here, right? j1 square. Here, j1 square commute any component, so that is there. And then this one also commute because it is independent in this case, right? j1 to any j2. So immediately we got this 0. And that means the jz commute with j1 square. And similarly, j2 square should be also same thing, right? So I just write that. j1z plus j2z. Also 0. So we have this. Now we are going to look how about the j square with j1 square. Now you see here, which one we have j1 square? We have 3 equations, right? Equation 1, equation 2, equation 2 prime. Which one we are going to use? It's better because this is relation between the first one, right? j1, yes, in terms of each individual, right? So now let's write down here. Let's write down j1, j is j1 square plus j2 square plus 2 j1z, j2z, and plus j1 plus minus plus j2 minus and plus j1 minus j2 plus with j1 square. Now, I don't need to do it. So you can j1 square commute j1 square, right? j1 square commute with j2 square. So those are here. And then J1 square combined with J1z, definitely also J2z, and also others. So I immediately consider. You agree? Okay. Now, so far, similarly, we can also prove J square with J2 square is also commute. So now we can see, you can see how many operators? J square, Jz, J1z, J1 square, J2 square, right? So we have J square, Jz, J1 square, J2 square. They mutually commute. If you mutually commute, I think I don't need, I can erase this part, right? This part. But you may say, I know J1 square commute with J1z, J2 square commute with J2z, and J1 square also commute with J2z. So, but how about J square with J1z or J2z? Maybe we miss some others, so let's double check. Check which one, let's consider, okay. Check. Just select one of them now. J square with J1z. Let's see if J square commute with J1z. Again, we can substitute use this equation here, right? Yeah. It's J1 square plus J2 square plus 2 J1z, J2z plus J1 plus J2 minus and plus J1 minus J2 plus. That is J square and J1z, right? Okay. So now the only difference is J1z commute with J1 square, J2 square, J1z, J2z. But here, J1z does not commute J1 plus, right? So then we have a two term. It's J1 plus J2 minus plus J1 minus J2 plus J1z. Then we are going to use here. J1z with J1 plus minus give us again J1 plus minus, right? So I just do the same thing for you since this chapter 2, how to work on this product of the commutator. This one is this, so we have a product. So I take the first one, J2 minus J1z plus J1 plus J1z, J2 minus, right? The first term. This J1z is a product, so then you first take this outside with the second one, commutator, and then keep this one and this in the right hand side go keep here. Similar for second one, so that is J1 minus J2 plus J1z plus J1 minus J1z, J2 plus. Here, this commute, because this J2, J1, so that is 0. This is 0, but this one, we need to use this. So that is J plus, J1 plus J1, so that's just reverse, right? So we have equal to negative h bar J1 is plus, so that gives a plus, right? Plus. And multiply J2 minus this term. This one is J1 is again use this one. So that is a J1 minus, so that's a plus h bar J1 minus J2 plus. They do not commute, right? You cannot cancel this term. This is J1 plus multiply J2 minus, this is J1 minus multiply J2 plus. Similarly, we will J square, J2Z also do not commute. So yes, only these four mutually commute. The others, another J1Z, J2Z do not commute with this four operator. Do not commute one of them, right? J square. So the others, it commute JZ, right? Because JZ is J1Z plus JZ. So commute with it, commute this, but not commute this one. So they have take off those. So now we found, okay, we have four operators. They are mutually commute. This is a commutation relation we found between the total angular momentum and each individual. So we answered the question, that is 3, right? Commutation. Now we go to next question. If we know this has a joint, they mutually commute each other, so now we go to that's question number 4, right? Number 4, we are going to find the eigenvalues of G square and Gz. Since we know J1 square, J2 square, that we already know. Suppose given J1, J2, how about this total, right? So that's how to obtain this. Now first, because, right, so now we know this J square, J1 square, J2 square, and Jz mutually commute. Right? So this they have a common or joint eigenstate. This joint eigenstates, we are going to use this index J. This J is the quantum number for J square, right? And then the M is quantum number for Jz. Then the J1 square, J2 square, which is J1 and J2. Since let the order follow the text. Since J1, J2 is given, right? So now let's write down first. J1, J2, and then for given J1, J2, we have a value J and M. So this one is joint eigenstates. Then, of course, how to get it later we are going to discuss. But this is give us, we introduce the quantum number J and M correspond to the quantum number J square and Jz. J1 and J2 is quantum number J1 square and J2 square. Okay. Just to remind you, for each individual, right, the chapter 5. For this one, for J1, right, this is the eigenstates of J1, that H bar square J1 plus 1, right? J1, sorry, M1. And the J by Z, H bar M1, J1, M1, right? That is for each individual. That is eigenstate, so this is the M1. So they form 2J1 plus 1 subspace, as I already discussed before. In this subspace, this eigenstates is formed by J1 and 1. Right? That is this subspace formed by this eigenvectors. Similarly, J2 square, J2 M2, and J2Z J2, M2 also given because it's eigenstate. So we know this. M2, J2, M2. So M2 is J2 and 2, and then this eigenstates J2, M2 is formed another subspace 2, J2 plus 1 subspace. Then since they are each individual, then all right. Do you agree? J1 square, J2 square, J1z, J2z, they are also mutually commutative. Right? As I here for each individual, right? So the J square, J1 square definitely commute any operator J2, J2 square, J2z, and J1 square commute with J1z. J2 square commute with J2z and also others, so they form the joint eigenstate. So the joint eigenstate of this form. We have a two group, right? The first group is J square, J1 square, J2 square, Jz. Another group, we also found another four operators, they are commute each other, J1 square, J2 square, J1z, J2z. And this one, we are going to use J1, J2, M1, M2, which is, since they are in this different subspace, so we can, this is just products of these two. So I use J1, J2 also in font to follow this because that means once we define J1, J2, then what will happen is addition of 2. So when we have J1, J2, M1, M2 follow this, then there are also formed space. So how many? 2J1 plus 1 subspace multiplied 2J2 plus 1, right? That is dimension is space of addition of J and plus 2. We agree? So if we have two angular momenta, and then each individual form the subspace. So when they put together, this, since they are independent each other, so joint eigenstates is the product of each individual. So you see the space depends on how much value of M2 and M1 it is from this. And for this group, this eigenstate they form the orthonormal, so that and the completeness, so that is J1, J2, M1, M2, J1. Now J1, J2 is fixed, but M1, M2, maybe M1 prime, M2 prime, since this, for giving J1, J2, we have a choice of M1, M2. So the inner product of these two, one of these two from here, that gave us, it is orthonormal since that is J1, M1, J1, M1 prime, J2, M2, J2, M2 prime. And that gave us M1 be equal to M1 prime, M2 equal to M2 prime, right? Only when they equal, then that is non-zero, otherwise 0. So that is also, and then this completeness, if we sum over all the M1 from minus J1 to J2, J1, and that is this one, J1. We sum of all the possible M1 value, M2 value. That means all these states, right? That is J1, J2, M1, M2, CAD, and draw J1, J2, M1, M2. That's be equal to identity operator, the completeness. So that means this a group of the joint eigenspace formed 2 J1 plus 1 multiplied 2 J2 plus 1. The whole space, the add together is equal to this one. That is the property of this group. So we have a group 1. We have this property. Now let's come back to here. The reason one is because this one we know, since for each individual angular momentum, we know each individual, right? So that is we can immediately got this result. Then we are going to use that relation to find the joint eigenstates of this form. Then we can find this eigenvalue. So that is the space. Now, okay. I think okay. Just take one of the numbers, you know. If it is a joint eigenstates, so we suppose J y square apply to J1, J2, M1, M2. As Zhang just asked me before, when the operator applied this, the whole wave function, there's a radial part and angular part. So it only depends on, so now let me write down this one. J1 square, J1, M1, J2, M2. Now, J1 only apply act on this subspace J1, M1, right? It will not apply this. So then you know this one will give a H bar square J1, J1 plus 1, J1, M1, J2, M2. Then you can go back H bar square J1, J1 plus 1, J1, J2, M1, M2. So now for the combined or joint eigenstates, if we have the operator only work or act on one of these, the product of one of them, so you just work on that. This part, you just keep it. If we have a J2 square, apply this joint eigenstates, you just work on the second one. You can do this way, because you can move this to the second one, so that gives us H bar square J2 plus 1, then J1, M1, J2, M2, or finally J1 and J2 plus 1, J1, J2, M1, M2. Another one I just gave, how about the J plus minus? So if we have a J1 plus minus, apply this joint eigenstates. How to do that? Again, you just work on this one of these subspace J1 plus minus on the J1 M1 and the J2 M2. Just keep it. And on J1 M1, we know that is H bar square root H bar square root. So J1 minus plus M1, right? J1 plus minus M1 minus 1. And then J1 M1 plus minus 1. J2 M2. So it only acting on M1. So raise over lowering the M1 does not acting on M2. That is when we have this, if this eigenspace is just simply the product of each individual. So here then you can write this one, I can rewrite this way, H bar, J1 plus minus plus M1, J1 plus minus M1 minus 1. Now here, you write down this joint eigenstates is in terms of J1, J2. It will not change, only M1 change, right? So then here, M1 plus minus 1 and M2 keep here. So they are equivalent because they are each individual products are each individual. Okay, the remaining part like GZ1, G1Z, all the others you can follow the same thing. Now we are going to combine. So for this joint group, right? G square, GZ, G1 square, G2 square. Now we have to introduce the joint eigenstates is G1, G2, Gm. Then what that means, if this G is eigenvalue of, the quantum number of G square, M quantum number Zm, so then we know since this is already proved this angular momentum, right? So now when they apply this, here we cannot separate, right? Here it's always together. This only on the J, right? For J1, J2 is, so that is H bar square J, J plus 1, J1, J2, J. Yeah. That makes sense? Here. This is quantum number of this, or this is the joint eigenstate of this, so you can immediately use that eigenvalue here. And then Jz, J1, J2, Jm is H bar M, J1, J2, Jm. How about J1 square? J1, J2, Jm. Now J1 square only works on J1. So you just need H bar square J1, J1 plus 1. And since it will not change the quantum number, right? Similar J2 square, J1, J2, Jm is H bar square J2 plus 1. Then now how about this J plus minus? J plus minus Jx plus minus Ijy. It is not eigenstate of J plus minus, right? But we know since it is the eigenstate for total J square and Jz, so we immediately use the relation like here. But this is each individual, not its total. H bar, this is J, because this is work on J and M, right? So that is H bar, okay. G minus plus M, G plus minus M minus 1, J1, J2, G. But now, M, since it will receive the M quantum number either increase or decrease, so that is M plus minus 1. This is assume this joint eigenstate, so when the operator apply to this, you will have this result. Just follow like each individual, but the individual, if you deal with this joint eigenstate is individual, but if you look on this joint eigenstate, be careful here. It's total J, total M, if this is the total J square, total Jz, and total J plus minus. Right? But each J1 square, J2 square, that is still like the eigenvalue things. Now we are going to deal with what is allowed J and M value, right? So now here, this space, how many, what's the dimension of this? That dimension, is the dimension of the space. In the total angular momentum, that be the same with this one. Right, because this J1, J2, each individual has a subspace from the whole space. You just use a different basis set to describe the space. Like in the spatial, we have Cartesian coordinates, x, y, z. We have spherical coordinates, r, theta, phi. But all are 3 dimension, right? Dimension 3. So only different basis set you select. here the same thing. We describe the addition of G1 plus G2. So the space, the dimension of space, if we use this basis or G1 eigenstates, that already gave us that's 2G1 plus 1 multiplied to G2 plus 1. So here it is equal to this. Do you agree? Okay, so that is the information we are going to, and that is also equal to, since here, this is for giving, right? We always discuss for giving G1 and G2, and this one is fixed. Then we are going to discuss the allowed G value and the M value. So that is summation for G. Let's suppose we have a G max value, minimum, and G to maximum value allowed. And for each given G, we have a M from minus G to G, right? That is this summation, or summation from G minimum to G maximum. Since for each given G, we have a 2G plus 1. And that's equal to this. We have this relation. All right, so now with this relation, we are going to find what is allowed G value and the M value. Let's use a graphic, plot the graphic and help us to give the idea. Then we go to the algebra. So first, graphically, let's consider G1 is the G1 subspace. So if we have use this G1x, G1y, right? And then this is G1z. So the G is here, suppose this is G1. This value is G1 plus 1. Okay. Then we know the projection to this is a GZ, right? So that is, we can have a possible, because for given G1 we have a M1, so M1, dash all the possible value depend on G orientation, right? Suppose we have those. So that is M1 equal to G1 H bar, this is maximum. And then go to the here is equal to M1 H bar, right? And go to the lowest is M1 equal to minus G1 H bar. Okay, that's it. That's minus. So in general, it's like this, right? Follow this. Similarly, we have a G2 subspace G2x, G2y, and G2z. G2 H bar, G2 plus 1. Maybe they are not same, so assume, let's just assume that their components one Z is not same, right? Suppose we have only 4. So this case, this G2 H bar, this value, and this one is M2 H bar. This one is minus G2 H bar. Okay. So that's each individual we have. Each individual the angular momentum. Now, if we have the total, so G angular momentum is G1 plus G2, right? So graphically we know. Suppose this is G1 and this is a G2. So we know this is a G, right? So we have an angle between the G1, G2, and let's say alpha. Then how to determine this? Here we know the magnitude of each individual because that is quantum number H bar square root. But now how about this one? So this one is is according to this the law of cosine. So the the magnitude of J should be take this J1 square plus J2 square and plus J1 J2 cosine alpha, right? Let's give us. For arbitrary 2 J1, J2, we have angle, so we can see the magnitudes depend on how much the big J, and that be correspond to J plus 1. Or we're going to find what is value of this one. Now, this is case 1. So, for example, if we have J1 to the left and J2 to the right. So the addition of these two together is here, right? This is a J. But here you see this is definitely minimum, right? When the two angular momentum the opposite direction, so you have this J, in this case minimum, that is J minimum is just a square root of J1 square minus J2 square. Because here alpha is pi. So when pi cosine pi is negative, so we have negative sign here, right? So that is this one. And that is minimum. But if the J1, J2 are same direction, so the total is J maximum. That means if they have the same direction, we will have a maximum J value is just simply J1 square plus J2 square. Okay, this is this case, this is alpha equal to 0, this alpha equal to pi. So what does mean? That means the J value here depends on the angle between these J1, J2. Then there's a range, so J, allowed J value for given J1, J2 must be within this one, right? Then we are going to find how to determine this. Then between this one, J value increase only by 1 unit. So if we know J minus, J plus, J maximum, then we know each individual J allowed value. Let's keep here, then we can continue discuss. To determine this, we are going to use this relation and this picture that can help. All right. Yes, if you want to finish your homework too, you can tell me. If not, the next Monday is also fine. Give you the time.
Thank you.
Okay.
My first thought is that's a lot of J's.
Lot of J's. So now which one? J1, J2. J maximum, J minimum, yes. So since we have more angular momentum here, how about addition 3, then J1, J2, J3, and yeah, J1, 2, J2, or J1, 3, that's the index. But if you notice, the last one, I just gave you, I already posted the solution, right? On Blackboard, the problem 3. But it's L equal to 1. L equal to 0, you're all fine. L equal to 1, I just post solution so you can check that one and see. You just, the formula for J1 and N1, you use the J0, N0. So that, then you add the remaining part is, yeah. But the idea is okay. Just the formula, yeah.
Oh, go really.
At the beginning. Yeah. practice, but then we have the build up ourselves. That's more experience to deal with the company of finance.